The fourth reaction is hydration. Hydration means the addition of water to hydrate. And in that, you add an alcohol, an OH, a hydroxy group, as you see in the reaction in front of you. So if you take a look, you notice that via these reagents, an acid, you add OH. And once again, notice how it is added to the more substituted, the water, the hydroxy is added to the more substituted carbon. Or the one that has less H's. Now, before we begin, you may get these reagents written differently. They may be written sometimes like this. H2O and H2SO4. So if you recall, H2SO4 is a strong acid. And the reaction of water and acid would make H3O plus hydronium ion. So again, this means again you're making hydronium ion just like it is here. So let's look at the mechanism. The mechanism is you have your hydronium ion that will react with the double bond. So the double bond is electron rich. What it will do is that it will attack the proton. The electrons are going to go back to O. And let's say here's the H. We understand before there's an H, so we'll show that for clarity. Now, this is following Markovnikov's rule because it will create a carbocation. So we followed Markovnikov's rule. Where we add H to the one with more H's. Very well. The next step would simply be that now you have water. That is nucleophilic due to the lone pair. And this water with its lone pair is going to attack the carbon, electrophilic carbon, where the carbocation is. And water now will be added. But as you're aware, is that water with 3 bonds gives you an oxygen with a positive charge. So we always need, just be always aware that you always need to remove an H from water to make it OH. So in this case, you have another water molecule. That will deprotonate the hydrogen, the proton here, and you will end up with this product. Now I drew it, of course, slightly differently than above. It's the same thing. So again, you add water where it's more substituted. You follow Markovnikov's rule because you have a carbocation. Now the next reaction is simply another route to get the same product. So this is called oxymercuration. And it's just another route to help you get an alcohol. We're not going to do the mechanism on it, but just again, make sure you again follow Markovnikov's rule as well. So if I give you this example, with mercury diacetate, this is acetic acid, and sodium borohydride as the second step. There is a mechanism for this, but we're not going to study it. Once again, you need to see where it has, again, the less H's. So there's an H here, and there are no H's. So our product will be like that. Now, be aware that you may get a racemic mixture here. Very well. So as we're going through them quickly, the rest of these, we do not need to know the mechanisms. Just again, be able to apply the reactions. If you're given a new reaction, again, go from one example to another. The second one is called anti-Markovnikov's hydration, and that's usually what we call a hydroboration. Reaction. So this one is anti-Markovnikov's, meaning again, you're going to add the OH with, so let me write that down, OH now goes with more H's, where you have with carbon, or goes with the more H's. You know what I mean. So if you look here, there's an H there. Since it's anti-Markovnikov, that's where you add your OH. So again, make sure you remember Markovnikov, and if you know what Markovnikov's rule is, you know what anti, it's the opposite. So therefore, here's the product. So if I just apply it to, there is a complicated mechanism for this, so I'm not going to go over it. But once again, this one has an H. This one has no H's, no hydrogens. So therefore, I'm going to add my hydroxy group to this carbon right there. Add OH. So therefore, this would give me right here. Of course, if I use these reagents to be boron trihydride, THF, it's a solvent, and of course, that's the second step. It's a peroxide and sodium hydroxide. Once again, you have a racemic mixture here. Cyclopropane formation. So as you see here, you have a cyclopropane formed. This is what cyclopropane is. It's a three-membered ring, carbons in there. And if you see, it's formed right there. It replaced the double bond. The only difference is these are halogens. So this can be written as CHCl3 or CHBr3. Generally, these are the ones that are associated with this reaction. So again, as you see, you can see you have a three-membered ring. Now, if you notice, this cyclopropane ring with its halogens attached to it, if you notice that these bonds are coming outward, coming towards you, or they can go in. Either or, this has to be indicated. So if I have a simple reaction like this, and I have these CHCl3, which is chloroform, KOH, then this is how I would draw the ring. Now, you don't have to put the C. I mean, that is usually indicated. I'll show you how you don't have to include them. You just have to, again, and now you have to put both of these halogens, which are Cl. So you have SCl and SCl. Whatever halogens are attached to this, what we call haloform, which is in this case a chloroform, these are the atoms added. Of course, we have the methyl group right there. This is another similar reaction. It's a cyclopropane formation, except you don't have halogens attached to the carbon in that cyclopropane ring. You have hydrogens. It's called the Simonsmith cyclopropane formation. So if you notice, the reagents are different. Once again, you are making a cyclopropane ring. So this is diiodomethane, zinc, copper. It's an oxidation reduction reaction that's happening between the zinc and the copper. And once again, okay, let me make this a little bit cleaner. And you don't have to show the H's because we know they're there. Now, this is a very important reaction. This is a reduction reaction. And what is happening is you're getting rid of the double bond completely by going from unsaturated to saturated hydrocarbons. If you notice here, the double bond has been replaced with single bonds. They may not be there. Let's show them. Now you have two H's, and we have to indicate this, is that those H's are on the same side. Of course, we will make the adjustment later in this case. So if you notice here, you have hydrogen gas over a palladium. Sometimes it could be platinum, sometimes it could be nickel, over a transition metal here. Now, the mechanism for this is quite involved, but before we begin, it's basically you have a metal sheet and hydrogen gas is H2. So you have those metal atoms with the H's attached to them. And you put that in a balloon. Basically, you have a balloon, you put it in the reaction flask, you stick it with a needle attached to the balloon, and it goes in the reaction flask. Of course, it's closed with something called a septum. And what happens is that for an alkene, is that notice that the reaction adds to the same side. That's why I put those H's on the same side. And that's why it's a reduction reaction. Again, you are eliminating the carbon-carbon bonds and you're adding carbon-hydrogen bonds. So there's plenty of this. As simple as this, all you have to do is, if you ever see this reaction, sometimes the PD over charcoal is written on the bottom or to the side, it doesn't matter. It could be another, is you get rid of the double bonds. Now, sometimes I may include excess, sometimes I may not. So I'll put excess just to tell the students, but generally you have enough hydrogens to get rid of multiple and multiple double bonds. So if I have, waiting on this. So if I have H2PDC, and I'll make it easier for you. I'll say in excess, then once again, you have no more double bonds attached. They were all reduced or they became polyunsaturated to all saturated. This is the process that they use in making hydrogenated oils, vegetable oils, which is actually a bad process health-wise, because again, it goes from unsaturated to saturated. They do that because again, it just makes the oils in this case more saturated, better for storage, and they just more economical for them as well, for the manufacturers. But you know, too much saturated fats are bad for your health. So we're getting close. I'm going to finish all in one video. Epoxidation is you're making an epoxide. An epoxide is kind of like a cyclopropane ring, except you have an oxygen right there. So this is called an epoxide. What you have here is you have this reagent, and this is an R group. So I'll give you an example of that. So you may have something like CH3. Let me just delete that for a second. That's the structure for the RCO3H. And if you look at it, structurally, again, the R group can be whatever is attached to it here. So again, you make an epoxide. So you have this, and let's say you have this one right here, CH3 as a mechanism, as a reagent. You're making an epoxide. Right there. Hydroxylation. Hydroxylation is adding two alcohol groups same side to the same side, or this is a syn addition. So you have osmium oxide, and of course you have these other reagents. All of them would give you, again, this is another helpful reaction where we can add two hydroxy groups, alcohol groups, to the same side. Again, this is syn addition to the same side. Once again, if I have this, then what I am doing is I am adding the OH to the same side. Same side. Osmium oxide is a very dangerous reagent. Osmium, especially to the eyes, it causes blindness because it forms a coat that covers the pupil and can no longer see. And it's very expensive metal because it's very rare. We're getting close to the end. So you have ozonolysis, which is adding ozone. And when you add ozone to alkenes, you form aldehydes and ketones. So in this case, this helps you make aldehydes and ketones. So if you notice, formation. You might say, why have we been talking about all of these reactions? Every reaction yields something new to you. Like if we begin even from all the way with first reaction. First reaction, we went from an alkene to an alkyl halide, following Markovnikov's rule. Second one is the same thing, anti-Markovnikov's rule. Third reaction, we also made the halogenation. We also made an alkyl halide, but again, with both of those halogens, with two of those halogens atoms added. Here we formed a halohydrin, an alcohol. We went from an alkene to an alcohol. Cyclopropane ring. Got rid of the double bond. We went from an alkene to an alkane. Made a diol. That's an alcohol. Again, two alcohol groups. That's a diol. And now you're making ketones and aldehydes. So these are the reagents. Quickly, all you're doing here with this reaction, and I'm going to make it easy for you, there's quite a complicated mechanism, is that you're going to do the following. You're going to cut this double bond in half, And now you're going to add an oxygen to make it a carbonyl, as you see on the other side right here. So if you notice how there was an oxygen made. So the shortcut is the following. I'll make this bigger. Again, this is the double bond. You cut this in half and you add an oxygen right there. Of course, you can draw it like this. Some students do draw it like this. I mean, momentarily, you know, you can do that, but it is not, again, we have to make it look like, again, it has a trigonal planar geometry. So let me show you with another example. So again, if we have something as simple as this versus, and you'll see the aldehydes and the ketones, as you probably already saw them here. This is a ketone, and this is an aldehyde. But since this is a cyclic ring, they're all in one structure, but they can be in two structures. So if I treat this with ozone, again, either one of these, the zinc and the acid, or the sulfide here, here's what you do. Again, you divide this in half. And again, you're supposed to make this a carbonyl and that a carbonyl. So watch the transformation. So it should look like this now. I'm going to start with this side. And that's fine to draw this one this way. And that side. Okay. Now, of course, I showed the H here, so I am going to show it as a reference point here and to show you the formation of an aldehyde. So this is an aldehyde, and this is a ketone. Well, what if you had this? Well, you will make 2 moles of an aldehyde. Of course, 2 different ones. I'm going to show them right there because it's a positive sign here, so plus. So you have 2 different aldehydes being made. And finally, the oxidative cleavage can make plenty of products. Depending on what you have, you can make ketones, and you can make carboxylic acids. So here is another useful reaction for us. How did we make, here's the key for this. For permanganate, it's an oxidizing agent. It's a very, very powerful oxidizing agent. We learned about this in Gen Chem. you have an H here. So this is similar to the last one. You're going to cleave, cut this in half. You're going to form a carbonyl, but with one difference here, is that this is such an oxidizing agent, such a powerful oxidizing agent, that those H's are not going to remain as aldehydes, as part of the aldehydes. They too will be oxidized. So in this case, the idea here, and I'm going to show you with an example till this one stops freezing. All right. Is that, again, make this an OH. As you can see here, what happened. All right, so let's look at our example. I'm going to put the H right there so you can see it. So here is permanganate, potassium permanganate, hot, concentrated, etc. And then, of course, you have an acid. So the key is you cut this in half. And you will make right there. But again, you have to make this an OH. So what you made here is you made a ketone and you made a carboxylic acid. What if you have be careful again, look at the alkene that you have. You will make now only carboxylic acid. So again, be aware of that. Make sure you are aware. These are the only reactions that I want you to know. I know there are plenty more reactions with the epoxides. We may get to them a little bit later, but for now, these are the reactions that I want you to be able to apply as you see how I applied this to a new example.